Today we'll begin Unit 3, Newton's Laws. With Newton's Laws, we actually begin not describing motion, but how the motion actually began. Um, and with that, it's not just, again, it's moving. That's what the previous units have been looking at, in motion in one direction and motion in two directions. But now we begin talking about, okay, it's moving. Did it start moving is really what becomes with Newton's laws. And the main reason why we say that science can suck is because that is, all forces are a push or a pull. And that is how all forces are described in the realm of science, so that all forces are either a push or a pull. And a force is always necessary to get it started, of some sort. If you want a force is also necessary to change the velocity of that object. Now the magnitude is usually using a spring scale, as we can kind of see in the picture here. This is a rudimentary spring scale. In the classroom, it's the thing that you can also have spring scales that will look like dials or a clock in itself. I usually have one at the front of my classroom, that works pretty well. I think it's only about a 10 or a 12 Newton scale. Sometimes spring scales can be have different abilities. Some will measure only to a maximum of 2.5 newtons. Some of them will measure to 20 newtons, and a lot of that will based on there. We also have access to some Vernier software that will allow us to get a digital readout of those, instead of trying to use a spring scale, or a plunger system is sometimes what is also used with that. And one of the first people that we talk about is that the great scientist Galileo Galilei. A lot of times is credited and looked at in a lot of astronomy because of what he did for astronomy. But he also looked at and gave us some other and our beginnings of actually describing motion a little bit differently, or a little more thoroughly, which will allow us then to kind of work with some stuff. And it kind of gives Sir Isaac Newton some ideas and things such as that. Galilei was not always a big fan of the kind of the church at the time, the Catholic Church at the time of Galileo. He had some very controversial thoughts, and that is the sun is the center of the solar system, and that the planets rotate around it. We look at that now as like, well, what? Of course that's the case. But you have to understand, for many times you have, and this is why there's still people out there that believe that the world is still flat, because for so many years that's what we thought, and therefore all of this other stuff is just people trying to change our mind as well. But nevertheless, Galileo begins our talk, and this is why I say we can talk a little bit. It's the most history that we get into, really, with the general physics class. Now, Galileo says that if I have a ball go down a ramp, it will go up a similar ramp to that, and should go up to the same height or very close to it. Doesn't always work that way because we know of another force, and that is friction. As we go through this, and a ball such as that would go up a ramp of similar steepness or slope and would go up that same thing. Now, a ball at a lower angle or less slope would go slower, as we've seen even through our experimentation. But Galileo actually wrote it down, so you write it down, you get credit for it. That's why science works the way it does. As we go through, it's the even less slope. It is going to have even less acceleration, or have less velocity as it goes down. But still, the idea is that it would go up a ramp very similar to the same height. Again, doesn't always happen that way because of other forces. And so we would be able to kind of have that same thing. A ramp going in the opposite direction is now going to then have it flip the direction of the velocity and also the acceleration. So what Galileo then also said, that an object at rest stays at rest, and an object in motion stays in motion at a constant speed in a straight line unless acted upon by a net force. Now this might sound very similar to somebody else's law on motion, and you would be correct in that it was kind of a piggyback on another law that we're going to look at mainly today. But this is what you kind of deal with, is that a rock would stay there until something acts on that rock till it falls down. Kind of natural law with that. And so those are some things that we have. Those are some of the things that we kind of go with on there. So it is a basic understanding in that an object, if I take an object and I roll it, it's going to keep moving until something acts on it. Now, what's acting on it and why even if you go out to a hockey rink right now, you can slide a puck across the ice. It's eventually going to stop. One, it's going to hit a board. That's a net force. Hitting something is going to be a net force. Okay? And then you're also going to have, depending on how large of a force you acted on it, is going to have an effect on how far it will go. Because again, you have to therefore understand that even on ice, even after a Zamboni's gone over it, it's still going to have friction, and so even then you're going to have that play in. Now, we saw it a little bit with the air tracks. As the air track was bouncing, it did not bounce all the way up, and so it loses a little bit of its elasticity as it bounces back and forth. And so though a lot of those are net forces, and some of those forces, and this is where things can get very complicated very quickly, and why we don't want to engineer it up too much. Like I said, friction is a big force, and friction is a force that is always there. It's really nice. I know a couple weeks ago, we didn't have a lot of friction on our roads, and sometimes some people are dealing with that right now currently. Not having a great amount of friction on their roads, and that's bad. You want to have friction. You want to have a lot of friction for your car and vehicles as you're going around. Having extremely smooth surfaces, not always good. You want to have some friction there. That allows for gripping and less slipping. We do not want to be slipping when we are driving. Those are bad. It might seem fun at the time, or especially going around a corner on an icy road, you kind of can drift out a little bit like that. But it is something that it would have a problem. We would have a very difficult time uh, walking if it wasn't for friction. Um, I mean, just think about having to walk on ice is not always easy to do, and therefore, um, if you got you got a little friction, and that's why they have these yak tracks, or people put sand down. We put salt down to actually decrease the temperature at which uh, ice melts, and that's why at a certain degree it doesn't really help it at all. In some parts of the country, they don't even put salt down because it's not going to do anything, so they just put a lot of sand down. They put some salt in there as well, but they also put sand down to add some friction onto that. And so it's that very important thing. Friction is good, but sometimes friction gets to be very difficult and causes a lot of pain in physics and some of the problems in which we have. And friction can be just air resistance. And that's why sometimes we will say, you know what, let's just not worry about air resistance at this moment in time. So when we deal with friction, we're going to deal with friction of certain objects, and we'll get into that a little bit later. So we will talk with the birthday boy, so to speak, and that is Sir Isaac Newton. According to the Gregorian calendar, it is actually January 4th because of the whole moving of dates. Although we do always enjoy saying Sir Isaac Newton's birthday, and that's why I put it on the old calendar of December 25th. But Sir Isaac Newton, when he had a pandemic, he just invented calculus. So I don't know. I feel at least I wrote or at least used open source resources to write a physics book during my use of the pandemic. So I figured it's at least slightly close. So Newton's first law. I mean, Newton has 3 laws, and we kind of take each law at a time, and so we kind of don't get into everything. Newton's first law is very similar to Galileo's thoughts on motion, and that is, with no net force, there is no acceleration. If you have no acceleration, that means the object is moving at a constant velocity. And ultimately, then we get to say that an object at rest stays at rest, and an object at motion stays in motion at a constant speed. And there's kind of where you get the little bit difference. In a straight line, there's another difference, unless acted upon by a net force. And so there are some additions to Galileo's idea or understanding of motion and constant motion. And so we do have to remind ourselves of a lot of the things, in that an object at rest it has motion, it's just zero. And I think that becomes a different understanding of some of the stuff, in that an object in motion will continue to be in motion, and that can be a little bit difficult, because sometimes we want to think about that it's always moving, and but it's not. And those wonderful perpetual motion machines that say will always move, but we know that there will always be a net force acting upon it. They can get pretty darn close to trying to get rid of that, all the other net forces, but they are there. So we do need to be mindful of that. So Galileo stated that the tendency of a moving object is to keep moving. That's the natural force. and every a material object resists changes to their natural force. This idea is known as inertia. Inertia is a property that resists change in states. And you can think about inertia as if you've ever driven with a load of bricks or a load of dirt in the back of a pickup, that the vehicle takes longer to stop because it has more inertia. And so therefore you have to, and that is just that, and or an object that will stop a vehicle has more inertia than the other object that is moving sometimes. Newton's first law says that a force is not needed to keep the object in motion, and that's important, is that once I stop moving an object across and let my hand away from it, once that interaction is gone, the motion is no longer there. Or the Galileo said that motion should stop. Newton said no, it will keep moving until the net force ends up being zero. Meaning it's still going to move, it just might be slowing down. And now you have an acceleration, which means you have a force, which brings actually Newton into his second law, which we will talk about a little bit more later on with that. But it's a big idea that we have to do, and that's why, you know, Newton's first law is sometimes called that law of inertia. You know, it's actually Newton's first and third law of motion are pretty well known. An object in motion stays in motion, and an object at rest stays at rest until another net force acts upon it. That's the easy one. And then you have Newton's third law, that for every force there's an equal and opposite or for every action there's an equal and opposite reaction, except for a Chuck Norris roundhouse kick, in which there is no ever a equal or opposite of that. But then you also have Newton's second law, which actually brings in math into it, and it's not extremely difficult math. It's just that it begins that discussion of, all right, now we got more to deal with it. And that an object will accelerate force in the direction of the force. And this is where we get to say we will be teaching you about forces and becoming better Padawans.